first semester final as it gets closer to the first semester final. I don't want to waste time today talking about it. Okay? So, exponential growth functions today. Tomorrow will be exponential decay problems. Thursday will be E growth problems and growth and decay problems with using Euler's number. Next week, Monday, Tuesday, and Wednesday will be solving exponential and log problems. Okay? So, here we go, exponential log -1. Okay? So, the first check that you need to make to determine if a function is exponential or not is to look at where the variable is. Okay? If it's an exponential function, the variable has to be in the exponent spot. Has to. Okay? Gotta be up there. If it's not up there, it's not an exponential function. Y equals 17x cubed is not an exponential function because the variable is not in the exponent. Okay? That's the first check. The standard form of an exponential function is y equals a times b to the x power. Now, with that being said, a here is your starting value or your initial value. It's what you start with. Okay? When you have when you've gone 0 months or right when you start, it's your initial investment. It's what you start with. Okay? B is my growth or my decay factor. If it's a growth, B is going to be bigger than 1. If it's a decay, B is going to be smaller than 1. But you already knew that because you did these last year. And you did them back in October. Okay? Now, with the one rule that the exponent has to be in the variable, or I said that backwards. The variable has to be in the exponent. That's our one rule. Comes 2 conditions. Condition number 1 is that A cannot be 0. Okay? That's our first condition. A has to be something other than 0. It can be positive, it can be negative, it just can't be 0. It can be a fraction, it can be a whole number, it can be a decimal. It just can't be 0. Okay? Condition number 2 says that B has to be a positive number other than 1. Okay? So the rule is the variable's in the exponent. The conditions are A can't be 0, B's got to be positive, but it can't be 1. Okay? Anything else works out. As long as the rule and the 2 conditions are met. Okay? So, identify if the following functions are exponential. If the function is, state the initial value and the growth decay factor. If the function is not, state y. Okay? So in the first one, f of x equals 2 to the x power. Is that an exponential function? Lexi says no. Why do you say no?
Well, it's implying that A is.
No. A can't be 0. Okay, what's What's the rule to determine if it's an exponential function or not? Is the variable in the exponent? Yeah, so it's an exponential function. So what's my b value then? 2. Do we agree with 2? Right? 2 is the b value is the base of the exponent. So that's 2. Okay? The a value is the number that's in front of that's being multiplied. Can't be 0. So that means in this case it's got to be 1. Okay? Second one. Bless you, Mother. Exponential function, not an exponential function. Why not? No. The variable's not in the exponent. Variable's down below. Okay? So this one is a no. It's not an exponential because the variable isn't in the exponent. Okay? You try the other 3. Third one, exponential, not exponential. Yes or no? Yes, it is. Why? X is in the exponent is what I'm looking for there. Okay, so that makes it exponential. So what's my a value then? Like -3. What's my b value? 2.6, like 2.6. Excited about that one. Okay? Fourth one, exponential, not exponential. Where's the variable? In the exponent. So that makes it exponential. What's my a value? 10. What's my b value? No. Nope. Why is my b value not 6? Because it's a negative exponent. So how do I make that be a positive exponent? 1/6. I reciprocate that number, right? So this b value here is 1/6. Because of the negative exponent there, I got to reciprocate that value. Okay? Last one. Exponential, not exponential. That's an E. So is it exponential? I heard a yeah, and I heard a yeah, no.
If it is, then it's got to be f of b.
So because it's f of x, right?
Yeah, you gotta have that x in there.
You got to have an x in there. Where's the x in this equation? There isn't one, right? So is it exponential? No. There's no variable in that one at all. That's right. It's not x. But yes, E is Euler's number. We'll get to it on Thursday.
That's what I was saying.
Yes. Yes. But that's not the variable that we're looking for. We needed an x in that problem in that exponent spot if this was going to be exponential. Okay? So, let's get to graphing exponential functions. Okay? Today we're going to focus on exponential growth functions. exponential growth functions happen when b is bigger than positive 1. If b is greater than 1, then the graph will grow away from the asymptote as you move left to right. Now, for your standard f of x equals a times b to the x power, your horizontal asymptote is the y equals 0 line, otherwise known as the x-axis. Okay? Unlike rational functions, which we did before the break, exponential functions do not cross your horizontal asymptote anywhere. Okay? They will not cross anywhere. Okay? So, this graph looks like that. It's growing as I work left to right. It's going to go away from this gap right here is getting larger and larger and larger. That's what we mean by growing away from the horizontal asymptote. Okay? If I was working right to left, it would be getting closer to it. Okay? But it's getting away from it, so it's an exponential growth function. My domain here is all real numbers. There is no vertical asymptotes. There's no restrictions in my function. Okay? My range, that's the y values that I can get out of this. My range is y is greater than 0. Okay? Let's try graphing a function. Oh, so are these growth functions or not? I thought we were graphing right away, but we're apparently doing this. Okay? Number 1, is it a growth function? As I go left to right, do I go away from my horizontal asymptote? Because where would my horizontal asymptote would be like somewhere in here, right? Somewhere in there, right? So in the first one, it's not. It's getting closer to that horizontal asymptote, working left to right. Second one, that is. Because it's going away from as I work left to right. Next two, my horizontal asymptote would be like there and like there. Yes, no, no, yes. I don't know, I don't know. Yes, no. Okay. This one is a yes because it's getting farther and farther away. This one is a no because it's getting closer and closer as we work left to right. Okay. Now let's graph. Y equals 1/2 times 2 to the x power. How are we going to go about graphing these things? How can we graph these things? What? T-chart, right? If you don't know how to graph stuff, if you don't know the shortcut yet, you can always just plug points in, right? Yeah, so let's plug some points in. Now, but let's be smart about this as to what points we plug in. Okay? What's probably the easiest one to plug in? 0. Right? 0. So if I plug in 0 into my function, what is 2 to the 0 power? 2 to the 0 power is 1. Times 1/2 is 1/2. So that means I go through the point 0, comma, 1/2. Okay. What's the next easiest one to plug in? X value. 1. 2 to the first power. times 1/2. So I go through the point 1, comma 1. Give me another one. 2. X equals 2. 2 squared times 1/2. 3. 2 cubed. 8 times 1/2 is 4, right? YB. What's my horizontal asymptote in this case? Y equals 0?
Yeah.
Looks like it stays above because remember we said it can't cross. Right? So it stays above. So the domain of this function is all real numbers, and the range is y is greater than 0. It's always going to be y equals 0 until I change it. Okay? And I'll show you in a couple of slides how we change it. Okay? Yes, you can take it. So here's a cool little factoid that we have for all exponential functions in the form of f of x equals a times b to the x power. All of those functions will go through the point 0, comma a, 1, comma ab, 2, comma ab squared, 3, comma ab cubed, 4, comma ab to the fourth, and so on and so forth. They will also go through the points -1, comma a divided by b, -2 a divided by b squared, -3 a divided by b cubed, and so on and so forth. On top of that, they will always have the asymptote, the single horizontal asymptote, there's no vertical asymptote, of the x-axis. So, if I want to graph this function, first off, I'm going to determine what my a value is. What's my a value? 1/2. Whoa! Whoa! That's going to wake somebody up on the interwebs. If you're not awake now, wake up! What's my b value? My b value is 3. Okay? So, I'm going to go through the point 0, comma a, 1, comma ab, 2, comma ab squared, and -1, comma a divided by b. Right? Okay? So 0, comma a is what? 0 comma 1/2. 1 comma AB. What's A times B? 3/2, right? Two, comma, well, what's 3 squared? 9 times 1/2? 9/2, right? Which is what, 4.5? Right? -1. What's 1/2 divided by 3? Nope. Close though. 1/2 divided by 3? 1/6. Horizontal asymptote still is that right there. Still above. Domain. Range. Boom goes the diamond. Yeah, buddy? Okay. Yeah. Love it. You try that one. What's my A value? -1. What's my B value? 2. Okay. So 0 comma A is my first one, right? So 0 comma -1 is the first point that I go through. Agree. 1 comma A times B. So that's going to be -2. 2 comma A times B squared. -4. 3 comma A times B cubed. Be -8, right? -1 A divided by B, right? So that's -1/2. Still have there, but now they're all below, right? Domain is still all real numbers. As Lexi pointed out, is your domain ever not going to be all real numbers? No, it's always going to be all real numbers. Range, though, changes from y is greater than 0 to now it's y is less than 0. Okay? Just when you think you got it figured out, Freddie, what do? I go and I change stuff. Okay? Okay? So, we're going to translate that. Okay? So, A times B to the x minus h power, then plus k, translates the graph horizontally by h units. So this part right here is your left and right. Vertically, is your k. here's how you go about doing that. Okay. That's going to shift it 1 to the right. Because you got to think oppositely with x. Oops, that's red. I don't want that to be red. I want that to be green. Bless you. What's this one going to do? Shift it down 4. Now, if I were to think of this graph, I would think of non-shifted. It would look like that, correct? Okay. So my points then would be 0, 2, right? 0, A. 1, 6, right? 2, 18, right? Okay. Now I'm going to apply my shifts. My green shift does what? Does that change x or does that change y in a point? X. So 1 to the right means I'm going to add 1, right? So I'm going to add 1 to my x's. Four down. What does that shift? X or y? Y. And I'm going to subtract 4. So the point on my translated graph, that goes to the point 1, -2. This one goes to the point 2, +2. This one goes to the point 3, 14. What about -1? So that would be -1, 2/3, right? On my original? Okay. What's -1 + 1? 0. And what's 2/3 -4? -3 1/3? Okay. Now, if you think about it, we shifted, this red shift shifted everything on my graph down 4, right? Well, what's part of my graph? The ha, right? So the ha went from 0, y = 0, down to y = -4. Because that got shifted too. And now everything is above my ha. Domain is still all real numbers, because if I shift left or right, I'm not changing anything. Okay, so that's still all real numbers. But now what's my range? Say loud. Fantastic. Couldn't have said it better myself. Y is greater than -4. Yeah, buddy? Love it. Okay? Now, exponential problems bring with it different and distinct kinds of real-world application type problems. Okay? So, the first real-world application type problem is going to be compound interest. Okay? Tomorrow I'll give you a different kind of real-world application type problem. The next day I'll give you a different kind. I'm going to bring in different kinds every day so that you don't get overloaded with them. Okay? So, compound interest. If you invest something, or if you put money into a bank, or if you borrow money from a bank, or different kinds of things. What other ones do I have on here? Let me see. If you win some money, okay? Or if you collect some money and put it into the bank, or something like that. Okay? So, on there, A is the amount. Okay? It's the amount that you now have. That's A. Okay? P is your starting amount. Otherwise known as your initial investment. 1 is 1. R is your percent, or I should say interest rate. Side note on that, it's going to be given to you in the problem as a percent, but you're going to use it in the formula as a decimal. And so you remember, you have to divide by 100 or move the decimal point over 2 spots to the left. Okay? When you're going from a percent to a decimal, moving it over 2 spots to the left. T is your time. And in this formula, it's in years. Always in years. Okay? N is the number of times that your money is compounded. Meaning, it's the number of times that they apply the interest formula to give you some more money. Or the number of times that the organism grows. Right? Something along those lines. With me? Okay. So, it's always a good thing to remember what the formula is. You deposit $3,000 into an account that pays you 3.28% annual interest. Find the balance after 5 years if the interest is compounded monthly. Okay? So if we compound monthly, how much money are we going to have after we put $3,000 into the bank. Okay? Well, let's figure out what we all have here. So, what is my P value? What's my starting amount, the amount that I initially put into the bank? 3,000. What is my interest rate? So my rate is 3.28%, but oops, that's a bad percent. Oops, now I got to restart over again. 3.28%, but I'm going to use that as, what did you say, Ariel? But I'm going to use that in my account, or in the formula, as 0.0328. Okay? Time. How many years am I letting it sit there? 5 times. N. How many times is it compounded per year? No. 12. It's compounded monthly, so each year it's compounded 12 times. Okay? So, let's go to my formula then. A equals 3,000 times 1 plus 0.0328 divided by 12 to the 5 times 12 power. We might need a calculator for this one. Okay. Say add 3,000 times 1 plus, what do we say, 0.0328. Oops, I got an extra 0 in there. Whoa, whoa. What the? All right, we'll start over again. Okay, and then we compounded that monthly, and then we're going to take that to the 5 times 12 power. Yeah, buddy? Yeah, buddy. I get $3,533.85. Now, my question to you is this. What if I would have said, how much money did you make in interest? Then what's the answer? $533.85, because you got to take away that initial investment is how much we earned in interest. Okay? Just be knowing that that's a classic mathematical type problem where they say not what's in the account now, but how much money did you make over the course of that time frame. Okay? Now, the wonderful thing about this is that while I was sitting poolside doing mathematics last week, I made up worksheets for you. Because I told you we were done using the books the rest of the semester. And I want to live up to that.